Hello and welcome to week 5 of Calculus 3. This week we are going to begin talking about what a derivative for a multivariable function looks like. We're actually going to have a few different kinds of derivatives, and we're going to start today talking about what is known as a partial derivative. Okay, so to start things off, we're going to return back to that original function f of v theta, which was measuring the horizontal distance traveled by a launched object with initial velocity v and at an initial angle theta. So when we first encountered this function, we were looking at it in terms of traces. So what we defined as a trace was when we fixed a certain variable at a certain value. So for example, we could look at the trace when our v was equal to, say, 200. When we did this, we had f of 200 comma theta, and this ended up being a quadratic function, a sinusoidal function, where we had sine of 2 theta times v squared divided by 32. On the other hand, when we fixed our theta to be equal to pi over 6, we had a function f of v comma pi over 6, where we ended up having v squared divided by 32 times sine of pi over 3, which is the square root of 3 over 2. So in the case of the first trace of when v was equal to 200, we had a sinusoidal graph. And this can be seen when I look at v equals to 200 and I look at the trace when I slice at v equal to 200, versus if I look at the trace for when I fix pi over 6, the trace that I end up getting is one that looks like this. So pi over 6 is going to be slightly smaller than 1/2. And so we're going to get a trace that looks like this. So in the case of this question, what we're asking at this point is, okay, suppose I started at this point. So suppose I'm sitting, this is some sort of a mountain or a hill, and I'm existing at this point, and maybe not even there. Maybe let's just, let's say. So suppose that I am at this point of 200 comma pi over 2, or pi over 6. What happens? What is my rate of change as I go down the hill? Well, here, when we're talking about this surface, there are lots of different directions that I could go. I could go down this way, I could go up that way, down, up, etc. I could even go on this diagonal. There are lots of different paths that I can take from this point that's going to result in a different rate of change. Our rate of change of elevation is going to depend on two things. It's going to depend, number one, on where we start. So first thing, if I start maybe say at this point versus this point, my experience traveling down the hill is going to be very different. Up at this point, I'm going to have much steeper directions versus at this point, it seems a little bit more flat. And so my change in elevation or altitude isn't going to be that different. It also depends on which direction we go. So I could travel this way, I could travel this way, I could travel down over that way. There are lots of different directions that I could take. Now, the second point is kind of unique to multivariable functions. When we were working in single variable functions in Math 111, our rate of change did depend on where we started, where we were looking at the instantaneous rate of change, but it didn't matter which direction we were going. We looked at the rate of change at that point. It was well defined by the slope of the tangent line. Whereas here, we have this issue of which direction are we going. So again, when we talked about rates of change in 111, it wasn't a concern because what we would have is some sort of a function that looks like this. I could have a single point, call it A, and I could easily define the tangent line at that point, and that would give me the rate of change at the point, say A, comma, f of A, where my function here is f of x. Direction and where I was going didn't matter. I had a single instantaneous rate of change at the point A. To start things off in talking about direction, we are going to simplify it a little bit and only talk about direction in terms of traces. Direction can go many different ways, and that's something that we're going to deal with later on. So to start things off, we're going to fix our trace like we did earlier when our theta was equal to pi over 6. Now, if we graph this in a slightly different plane, remember that when we plug in pi over 6, we end up getting a quadratic function, which is v squared divided by 200 times the square root of 3 over 2. While f is a multivariable function, when I fix my variable, I actually end up with a single variable function, which I could call h of v. And h of v is a quadratic, and if I graph it, so here this f of v here is my h of v, it's a quadratic that we know how to graph. It's going to look something like this. So here's my quadratic function, h of v. And if I look at a given point on my surface, I can translate that point onto my curve down here. And in this bottom picture, I can look at the instantaneous rate of change at this number. I can see that the instantaneous rate of change here can be found by looking at the tangent line at this point. We can do the exact same thing for when I fix v to be equal to 200. In that case, remember what we had was that our function ended up being 200 squared times sine of 2 theta divided by 32. And again, this is another function which I could call g of theta. It's a single variable function in this case. And I know that according to my picture here, I've got a nice trace when my v is equal to 200. And my function, again, rather than being two variable, is a single variable function, g of theta. Again, I can graph what this looks like. It looks something like this, where here I have, and I'm going to try to make this look a little bit nicer. So here's my function g of theta, where I-ish have a maximum at 0.75 according to the image that I have here. We could do this analytically using derivatives, but for now we're okay. And again, if I look at, say, this point here, I can have the instantaneous rate of change there. So this was a little smaller than 1/2. And I see that I can have that tangent line at this point. So while I don't have an idea of what derivatives are in this and rates of change are here, when I cut and I look at a rate of change at a point, I'm erasing that there, at a point, I do have that the instantaneous rate of change in terms of that trace is just the rate of change of my function in a single variable. The rate of change at this point here on our function of v, here we have that the rate of change is equal to h prime of v. We know how to take the derivative of a single variable function and evaluate the rate of change. Similarly, at this point on our trace in terms of theta, we have that the rate of change here, so rate of change, is going to be equal to our g prime of theta. So if I'm looking at rates of change in traces, this is relatively straightforward to define. All we need to use is our previous notion of a derivative for single variable functions. That brings us to the definition of a partial derivative. So a partial derivative is when we take the derivative so that the direction is with respect to traces. So I'm going to fix a value of x or y to give me a trace in y or x respectively. So here we have this f sub x comma ab is what we would call the partial derivative with respect to x, whereas for this f sub y, this is going to be the partial with respect to y. In the partial with respect to x, I am fixing here my value of y. My x is what is changing. So I have that x plus h. In the partial with respect to y, I have that my x value is fixed. I'm taking that y plus h in as my change. So I'm fixing x for the partial with respect to y. Just like we had here, I have that I am fixing a value of theta to give me a change in v versus fixing a value of v and then getting a change in theta. So let's try to look at this in that concrete example again. Remember that we have our f of v theta is equal to this function, and we said that when I fixed my 200 comma theta, I named this function g of theta, and this was equal to 200 squared sine of 2 theta divided by 32. And I also had that my, in the same way that I had that f of v comma pi over 6 resulted in a function of v, which was equal to, after some simplification, the square root of 3 v squared divided by 64. So these were my two traces when I fixed a value of v and fixed a value of theta. Both of these are functions that we know how to take the derivative of. We can say that our g prime of theta was going to be equal to, we in this case need to use a little bit of the chain rule. So I'll have that my g prime of theta will be 200 squared times 2, and then it'll be cosine of 2 theta. So I've run out of a little bit of room here. So here we have that our g prime of theta is equal to 200 squared times 2 cos of 2 theta. And I have that my h prime of v is going to be equal to, this is a little easier, 2 root 3 times v over 64. Both of these are functions that I know how to find the derivatives of. Now again, for this definition, what I see is that my value of v is what is changing. So this is just going to be equal to my h prime of 200. I have fixed a value of theta being pi over 6, so this is just h prime of 200. In the same way, here I've fixed my value of v, and so the rate of change here, this entire term, is just in terms of changing our theta value. So here, this is equal to g prime of pi over 6. Both of these are functions that we can evaluate and have evaluated the derivatives of. So h prime of 200 will be 2 square root of 3 divided by 64 times, we'll have our 200. So there's our v. And then for g prime of pi over 6, we will end up getting for our g prime, we have 200 squared times 2 cosine of 2 times our theta, which is pi over 6. So this leads us to a theorem, which now makes it easier so that we don't have to use this limit definition, hopefully ever again. So that is what we get here. So again, in the definition, the increment is added to x for the partial derivative of x versus the increment being added to y, and our x is held constant for the partial derivative with respect to y. So what we end up getting is that we can use a kind of Leibniz notation instead of this partial notation. You can use either one freely, where we're essentially saying that the partial with respect to x is the derivative of f with respect to x at this point, or you can have this partial f partial y at a point a comma b. The key here, and what we're going to see on the next slide and putting it into practice, is that when we're taking derivatives, partial derivatives, we treat the function, say we're taking the partial with respect to y, we treat this function as a function of y where our variable x is held constant. So we just view x as a constant because that's what we did in these examples. We viewed our variable theta as a constant and looked at the rate of change at that point. We thought of v as constant and looked at the rate of change at that point. And so with our computations, we're going to do the exact same thing. Let's go ahead and apply that idea to this function. So we have a multivariable function f of x, y, and our goal is to find the partial with respect to x and the partial derivative with respect to y. So to do this, to find what our df dx is, we are going to again treat our y as constant. And then that means that essentially to find the derivative, I'm going to view sine of y as a number and y here as a number. So it can get a little confusing. I end up getting that df by dx, here I have a number times x, so the derivative is just a number. The derivative will be sine of y, and then maybe it'll be helpful to say like 1 times x to the 1 minus 1 using our power rule. So here, this is constant in a way. And then for the next term, I have a sine of x times a number. So that number is still going to hang around. And then I have the derivative of sine of x is going to be cosine of x. So again, here, this is a constant. For our partial with respect to y, we do the exact same thing, except we are going to treat x as constant. So to find our fy, x comma y, we have that this is going to be equal to, now I'm treating my x as a constant. The derivative of sine of y will be cos of y. So I have x, a number, times cosine of y. And then for the second bit, I'm going to have that my y is my function. So I would have 1y to the 1 minus 1, which then my cos of x is again a constant, so it's just going to be there. That means I can simplify this to see that I get sine of y, x to the 1 minus 1 is just 1, plus y cos of x. And at the bottom, I have x cos of y, plus I have and that should be a sine. Sorry for that typo. So here, this should be sine of x, because that is just a constant. So here, this is a constant. And here, this is a constant. So we have that plus a just sine of x. For the second example, we are getting the partial derivatives at a point. So beyond finding the partial derivatives, we have to evaluate them at a point. So here we can have that our fx, our partial with respect to x, is going to be equal to, I take the derivative here, pretending that my y is constant. So I'm pretending y is a number. So I would take the derivative of e to the x squared plus y squared, have to use the chain rule here, times we'll have the derivative of the inside. So here, my 2x is a function of x, so I would have that it will be 2x for the derivative plus 0, because y squared is technically a constant. So that gives me my derivative at with respect to x, whereas my derivative with respect to y, I'll have e to the x squared plus y squared times the derivative of the inside, which here my x is constant, so my derivative of x squared would be 0 plus 2y. And then simplifying both of these, I get 2x e to the x squared plus y squared, and 2y e to the x squared plus y squared. And when we evaluate these at the points, we have that this will give us that f of sub x of 1 comma 2 will be equal to 2 times 1 times e to the 1 plus 4. And then for our partial derivative with respect to y, we plug in 1 comma 2. So we would get 2 times 2 e to the, again, 1 plus 4, which after simplifying gives me 2 e to the 5 for my partial derivative with respect to x, and 4 e to the 5 for my partial derivative with respect to y. We can also work with partial derivatives when we're talking about implicit functions. So for this function here, we can't solve for z and then take partials. What we can do is think of z here as a function of x and y, and take the partial derivatives with respect to whatever variable we want. So here we're trying to find z with respect to x at a point for this function. So in order to do that, because we're taking the partial with respect to x, our goal here is to again treat y as a constant. And we're going to take the partial with respect to x of both sides. So we'll have the partial with respect to x of cosine of 2xy plus z squared equal to the partial with respect to x of 1 over root 2. On the right-hand side, we have the derivative of a constant, which is always going to be 0. Note that if it were something with y over here, it would still be 0. But if it were something with x, it might not be 0. then it wouldn't be 0. On the other side, we take the derivative as we normally would. We have to use the chain rule. So the derivative of this in what we know, we would get sine of, and that would be a negative sign, keeping the inside the same, 2xy plus z squared, times the derivative of the inside. And the derivative of the inside here, taking the derivative of this, we would have that I have 2 times y is my constant, x, so the derivative will just be 2y. I have a linear function, the derivative is a constant, so we would get 2y. And then plus, here I'm taking the derivative of z squared. Z is a function of x and y, so but I'm treating my y as constant. So I'm going to have that this will be 2z and then dz dx, taking the partial with respect to x and using our chain rule, just like we did in 111. So now we're at this point, and we can go ahead and solve for dz dx because we see it in here. So this is what we wanted to solve for. And so we're going to fix our point. So at the point 0, 1, root pi over 2, we're going to have that negative sign of, we'll have 2 times 0 times 1, plus I'll have root pi over 2, and that's going to be all squared, times I'll have the 2 times 1 minus 2 times root pi over 2, and then that dz by dx. And this is all equal to 0. On the far left, we end up getting that this is just going to be negative sine of pi over 4. And then times, I get 2 minus, I'll have root pi dz dx, all equal to 0. I encourage you to pause the video just so I can save a little bit of time, finish up this expression solving for dz by dx. After a little bit of algebra, you should have gotten that our dz dx is equal to 2 over root pi. Again, the idea here and the key point is treating our z squared as an implicit function. So we're going to treat z implicitly and take the derivative as we normally would. So we would have that our d by dx of z squared was equal to, we use the chain rule, 2z, but then making sure to take the derivative of the inside. So that's going to be kind of z prime, which is dz by dx. Just as we discussed second derivatives for single variable functions, we can talk about second derivatives for multivariable functions. And we call that the second order partial derivative of a two variable function. And we do it in the exact same way. So when we were taking a partial with y, x was constant. When we took a partial with x, y was constant. So if I'm taking, say, fxx, that means I'm going to take the partial with x, and then I'm going to take that with respect to x again. Same with fyy, means we're taking the y partial and then the partial again. With xy, here we're taking, it's reading from left to right. So I take the partial with x, and then I take y. Here I take the partial with y, and then I take x. So here we're saying, just to write this out, this means x then y, versus this meaning y then x. This can get confusing when we switch back and forth between the partial notation and the Leibniz notation, because it's backwards. So if I want to read the Leibniz notation, I would have that it reads from right to left. So here, this means, again, I'm going this way. I take X and then I take Y, versus here, I do Y and then I take X. So just to summarize that, Leibniz reads from right, if I can spell right, right to left, whereas the subscript notation is from left to right. A little bit confusing, especially when we put it in this kind of notation where I need to read it this way. I take X and then I take Y, I take Y and then I take X. I want to give you a chance to do this. So for both of these functions, we need to compute all the partial derivatives. So we need to find fxx, we need fyy, we need fxy, and we need fyx. To do that first, it's probably a good idea to note what fx and fy are first, and then we can go from there. So pause the video, give this a try, and I'll be back with everything written out. So here are all the answers you should have gotten. For fxx in the first example, again, we're taking the derivative of the x partial derivative. So here, the partial derivative with respect to x, we're treating our y as constant. So this y cubed is a constant. So we just have 2x. Whereas if I take the derivative with respect to y, I'm treating my x squared as constant. So I just take the derivative of this. I don't need to use the chain rule. X squared is like a 5. And we just take the derivative of the stuff with y, treating the x as a number. Then once we take the derivatives with respect to x again, y again, and doing the different combinations, there are always going to be, for two variable functions, 4 total second order partial derivatives. And something that you may have noticed, and maybe because the theorem was here at the bottom, is that when we took the partial xy and the partial yx, in both examples, we ended up getting the exact same result. And this holds generally, and it's known as Clairaut's theorem. And it says that if we have a two-variable function and the partial derivatives are both continuous at a given point a, b, then we know that the partials are always going to be the same when we take them, the second order partials, xy versus yx, those are always going to be equivalent. The key idea in Math 111 when dealing with linear approximations was the idea that, well, if we look at a graph really, really close to a certain point, so let's say that we zoom in at this point A, so we have our point A comma f of A. At this point, our function is basically linear. We can zoom in really, really close and know that there's not that much of a difference between the tangent line and the given function. We also extended on this with our understanding of power series by looking at a degree 2 approximation using a quadratic to get concavity, and moving on to higher degrees to get a better approximation for the graph. So essentially here, if we zoom, right, so zooming, it's hard to see a difference. But we need to zoom in quite a bit in order to see a difference. When we want to extend this idea of zooming in and approximating a function by a line, how would we do that with a surface? The same idea of zooming in is relevant. So we're going to use the example surface of f of xy equal to 6 minus x squared over 2 minus y squared to help us build an understanding of what this zooming in looks like. So I've taken the graph of this function, f of xy, and zoomed in slightly. So here we get a kind of half zoom in. And then if we zoom in even more, we see that our shape would look something like this. Now, notice that when we zoom in, we start to lose curvature. So here we can see that there's a lot of curvature in our surface, just like here, there's a lot of curvature in our graph. But the more that we zoom in, the less that we see that change in the surface. And this is relevant to just how we exist on Earth. We live on a kind of bulging sphere and an ellipsoid, but on Earth, we perceive the Earth as flat. Here is a picture of some of the Canadian prairies that look very, very flat. We don't see the curvature on the Earth, versus if you go and find a YouTube video of people flying on a Concorde, which was the old supersonic plane. They don't fly anymore. Those planes went really, really high up in the sky, so high that you could actually begin to see a little bit of the curvature of the Earth. Even in a big jet that we take to travel across Canada, you don't see that curvature. You need to be quite far out to be able to see that we have and live on a curved surface. It's kind of not surprising that people thought that the Earth was flat, and some still do. We can recall from 2 weeks ago that we defined the tangent plane to be the following equation, where our constants a, b, and c were the coordinates, the components of the normal vector to the plane. And this was at a point x naught, y naught, z naught. Now, after moving things a little bit around, we can actually write the plane as a function of x and y in the following way. So we will get that z naught plus a x minus x naught plus b y minus y naught is equal to z. So here I've replaced little a for negative a over c and little b for negative b over c. The goal here is to determine, well, what would be good candidates for A and B? What need to be my essentially directions for a tangent plane? It seems that locally, I can look at the surface as a plane and find out what the coefficients for that plane would be. So below I have two images. I have the image of my surface, which is in purple, and my traces at a number, say, x naught, and a number, say, y naught. So here, and I'll change that to green to switch things up. So here is my y naught trace, and then I also have my x naught trace. Whereas in the second image, I'm doing the same thing, but kind of supposing that I have this tangent plane. And I can again look at x naught, which is going to give me that line. And similarly, I've got this y naught, which is going to give me this line. Now, if I intersect the plane with these traces, so here I'm intersecting the plane with, let's start with x naught. So that means that my plane I can rewrite as z equal to z naught plus, we'll have a times x naught and then minus x naught plus b times y minus y naught. And that means that this term here goes to 0, and all I'm left with is a function of y. I have z naught plus b times y minus y naught. This is a line where my b here is the slope. And we know, based on our understanding of partial derivatives, that the slope at this point should be equal to the partial with respect to y. So here we will end up getting that our b should be equal to the partial with respect to y at x naught, comma, y naught. I can look at the slope there, fixing my x naught, which will give me that slope there. And also will give me this slope here. We can do the same thing intersecting with y naught. So I would have same idea, z is equal to z naught plus I'll have a times x minus x naught plus b times intersecting with y naught, we get y naught minus y naught. And again, this entire term here at the end is going to go to 0, which will just leave me with z equal to z naught plus a times x minus x naught. And again, this is a line where my x is changing, my y is fixed. And so that is going to be represented by, again, this line here, or same thing, this line on the plane. We expect, based on what we know about partial derivatives, that when we're looking here, the change is going to be the partial derivative with respect to x at that point there. So we would have that our a should be equal to the partial derivative with respect to x at this point x naught, comma, y naught. We have a line and a point where that slope should be, and we know should be, the partial derivative at that point. We say that a multivariable function is differentiable if we can approximate that surface well by a tangent plane. So essentially that if we look at our surface, if locally it looks like a plane, then it's differentiable. That's how we define differentiability generally. Now, we have a theorem related to that about linearity and a linear approximation. If we have a function, f of xy, where both of our partial derivatives exist and are continuous around that point, so if we can find partials in both traces, then we have that the surface is differentiable and that tangent plane is going to be given by the following equation. So that little a is equal to our partial with respect to x at the point, and our b will be equal to the partial with respect to y at that point. And that linearization, rather than being a tangent line, is the tangent plane. So if we want to study the surface linearly, we study it by looking at the tangent plane at a given point. So from here, we can apply that definition to show that a given function is differentiable, and we can also find its linearization there. So here we have a polynomial function that we want to show is differentiable. And we can show that fxy is differentiable if we know that fx and fy are continuous. And this is a definition that we looked at last week. So here we can evaluate the partials, fxy and fy at xy individually. For the partial with respect to x, we have a constant, so it'll be 0, minus 2x plus another 0, because here minus 2y squared would be a constant. And then for the partial with respect to y, we have, again, a 0 plus a 0 minus a 4y. So we have 0 plus 0 minus 4y. Both of these, so both fx and fy are continuous at the point 1/2, comma 1. And so we have that our function is differentiable. So here, this means that fx comma y is differentiable. Awesome. So we've done the first part of the problem. Now we need to go ahead and find the linearization of the function. Okay, so we've done that. And now we can use this information to write out the linearization. We know that L of xy, by definition, is going to be equal to, we'll have f of 1/2 comma 1 plus the partial with respect to x at 1/2 comma 1. And then this will be x minus 1/2 plus the partial with respect to y at 1/2 comma 1, y minus 1. Then we can evaluate the partials and the function. So here this will be, I'll get 4 minus, I'll have a 1/2 squared minus 2. So there's my evaluating the curve, the surface. And then for my f sub x at 1/2, this will just give me a -1. So I'll have -1 times x minus 1/2. And then my fy, I'm going to plug in 1 here. So that's going to leave me with a -4 times y minus 1, which now simplifies to a nice 7/4 minus x minus 1/2 minus 4y minus 1. Now, if I want the linearization at this point, I'm going to plug in these numbers for my x and y. I'm going to get the output on the tangent plane at that point. So here we end up getting that we have that our L of 0.49, 1.25 is going to be equal to, we plug in these values. So we get 7/4 minus 0.49 minus 1/2 and minus 4 times 1.25 minus 1. I'll leave you to finish this up and find out that final value. But for me, leaving this in a calculator ready form is fine because I'm lazy. So again, just to emphasize what's going on here, I have my tangent plane. So if we want to draw out that tangent plane, so here's my plane. And then maybe if I can draw a plane, here we go. So here's my plane. I'm looking at the point given by 1/2 comma 1. And I have underneath of this plane some kind of a surface. So my surface might have some kind of a curvature. I don't know, but around the point, I have that my tangent plane is very, very close to the surface. And so then I can say, well, if I wanted to look at the point given by 0.49 comma 1.25, that's pretty close to the tangent plane. There's not going to be that much of a difference. And so if I can evaluate L at 0.49 comma 1.25, that is going to be approximately equal to f of 0.49 comma 1.25. To finish off this section, we're going to again rewind to 111 when we were talking about differentials. So suppose that we had a function, which I could call f of x, When we looked at f of x, we could also define the tangent line. So here I could look at the tangent line at a given point. I really like how that turned out there. That looks better. So here, this was going to be the tangent line at a point C. I could then move some distance away from C and look at a point C plus delta x. This distance here is what we called delta x, but we also labeled it as dx. Now, the d and the delta switch around when we're talking about the curve versus the tangent line. So we could also have, to switch colors here, I could look at the change in the tangent line. So my change in the tangent line is going to be here, and I'll label that in green. So here, this is my change in the tangent line, and that change in the tangent line is what we referred to as dy, whereas our change in the curve here, so this is the change in the curve, was our delta y. And we ended up coming up with a relationship between all of these quantities that our change in the tangent line was equal to the rate of change at the point x, or in this case c, times this dx. And again, those increments of delta x and delta y represented the change in height of the curve, whereas this dy is the change in height of the tangent line. And that change in height of the tangent line is what we called the differential of y. We can also define differentials with respect to two variable functions, where now our dz is going to be the change in the tangent plane. So here we have this df, which we could also call equal to dz, which is the change in the tangent plane. So change in the tangent plane height. We can also talk about changes in the tangent plane with respect to our independent variables of x and y, these being dy equal to delta y and dx equal to delta x. We'll define these more rigorously on the next slide. We define the differential dz as the vertical change in the tangent plane. So just like dy was the vertical change in the tangent line, dz, or you could also call it df, is going to be the vertical change in the tangent plane. And we can define this in a similar way to how we define the differential in 111, where we have that our dz is going to be equal to the partial times dx and the partial of y times dy. And we could also use a Leibniz notation to do this, so that it'll look like partial z x dx and then partial z with respect to y dy. So let's put this into an example. I have a curve given by this polynomial, and I want to find the differential dz. So to figure this out, we use the formula above. So we have that dz is going to be equal to fx of x comma y dx plus fy x comma y dy. And we can figure out the partials individually. Here I have that my partial with respect to x is going to be 3x squared plus 2y plus 0 dx. And I have that my partial with respect to y is going to be 0 plus I'll have a 2x minus 2y dy. And simplifying this, we get 3x squared plus 2y times dx, plus we have a 2x minus 2y dy. Now, again, going back to this previous image, we notice we have that df, and we also have delta f. Delta f is the vertical change in the surface. So again here, just to rewrite this, so df is the change in the surface. Just like it was the change in the curve for, delta y was the change in the curve f of x. And those changes aren't very different. We have that our dz is approximately equal to delta z. The change of the height in the tangent plane, especially when we're very close to a given point, is basically the same as the change in the surface. We can use that to help us with applied problems in terms of error. So here we have a problem of an automatic paper cutter cutting sheets of paper, but we know that production can cause length and width to be cut off by, in this case, at most 0.0 centimeters in width and at most 0.2 centimeters in height. We want to figure out, well, what kind of error are we going to get in terms of the area? How off are we going to be from the desired area of 200 centimeters squared? We can do that by looking at the function associated to area. So we know that a of x comma y is equal to x times y. That's what our area is always going to be. And so for our case, we know that we get a perfect area is going to be equal to a of 20 and 10, which is going to be equal to 200. 20 times 10. So this is, again, square centimeters. The uncertainty in our area, uncertain, if I can spell certainty, there we go, certainty, in the area is going to be equal to delta A, the change in the surface. And this is something that we don't know, but we can use the differential to help figure things out. So we know that delta A is approximately dA, which we have an equation for. We have that it would be equal to AX at 20, 10 times dx plus AY times 20, 10 dy. These are quantities that we can figure out. We know that our AX is just going to be equal to y, and our AY is equal to x. So AX at 20, 10 is going to be equal to 10, and then I've got dx, plus I have AY at 2010 will be 20, and then I have dy. Now, we have to think about what dx and dy are. Dx and dy are the changes in how far away we're going from that ideal point. So when we look back at this slide, we have our given point, x naught, y naught, which in our case is 10, 20. And we want to go some distance away from x naught, and we also need to go some distance away from y naught. And the maximum distance that we are going away from 20 is going to be, according to the information, will be 0.1. And the farthest away that we're going from our ideal height is going to be at most 0.2. And so we can replace our dx and our dy to be equal to 10 times 0.1 plus we have 20 times 0.2. And after a little bit of arithmetic, this will end up giving me 5 square centimeters as my change in A. I have an error of approximately 5 square centimeters in this situation. We can extend the ideas of linearization to functions beyond 2 variables. It's a little bit harder to visualize though, because we don't have a surface, we have a kind of volume, and this is really weird to think about. So the formulas though are always going to be exactly the same, except we're going to have an additional partial derivative because I have a function of x, y, and z. So I have the exact same term that I had for my linearization on a surface, plus that extra term accounting for the change of f with respect to z, because my function is a function of 3 variables. The differential dw, because I essentially have that my function here is equal to a function of w, I have that my differential is defined in the same way. We have the partials of our function with respect to the independent variables times our individual differentials delta x or dx, dy, and dz, where my dw is approximately going to be equal to delta w. The change in the surface is approximately the change in the tangent.